So I wanted to go over the homework quiz that used Coulomb's law with the superposition principle. The superposition principle being that you can take Coulomb's law and add it every time there is a new charge that is affecting the charge you're wondering about in terms of what is the net force acting on that charge. So just kind of going over the main solution that we showed in class. First, I gave a free check mark if you wrote the name on the paper. The only reason I did that was so that I ended up bringing up the total number of checks to 15 so that I could divide by 5 and make it a 3-point quiz. So the next check mark came from writing at least 4 of these 5 givens, and you had to identify the variables. One of the more common mistakes that I saw in writing the givens was that, yeah, people wrote the variables along with the charges, but they didn't end up actually naming this 1.2 meters. Like, well, what is that 1.2 meters? Is it some random distance, or is it actually some relevant distance that you need in the problem? So you only got the check mark if you ended up naming the 1.2 meters as R sub, well, some sort of subscript. And then we had the free body diagram, which was required. It was part of the question. And the check marks here are for having a force going down and to the left, another force going down and to the right, and finally another check mark was given for the fact that the force going down and to the left needed to be bigger than that going down and to the right, because if we go back to the original problem, we have this triangle over here. We're wondering what is the net force acting on this charge, and the magnitude of this charge over here is, and since the magnitude of the charge is bigger, that must mean that the magnitude of the force is bigger. And since these are attractive forces, there's a force down and to the left over here, big force down and to the right over here, smaller force because smaller charge. So getting back to the solution that we had, what we're going to realize is that you're going to need to add together the results of these forces. In other words, in this equation. Now, these check marks, these two right here, are for the correct applications of Coulomb's law in variable form. In other words, when you write an equation, you need to write it with variables only first before you plug in any numbers. That's something that is pretty much universally true on the AP exam in not just our class, but also in other AP Physics classes, and also, for the most part, in other AP Science classes when you need to use an equation. Now, these other two check marks are for recognizing that the attractive nature of these forces means that you need to put a minus sign in front of each of the unit vectors if you are solving this using the unit vector method. If you're not solving it using the unit vector method, then stay tuned, because I'm going to go through an alternative solution. But that's what these check marks are for if you solved it using the unit vector method. So here's where we are so far. And now it's time to start doing some math. We factored out a KQ1 and then plugged in numbers. And we got one big fat giant check mark for doing that. And notice I plugged in the unit vectors here as well. I would say that if you know your unit circle and all of the sine and cosine and tangent stuff with the unit circle, based on the fact that this was an equilateral triangle, these unit vectors are actually trivial and did not really require any significant calculation. They are definitely 1 unit long each, because that's just, these are all just different elements of the unit circle in terms of the I and j coefficients. But if you really wanted to show the calculation with sines and cosines, sure, that was fine. So then, start combining things together, and you got a check mark for essentially combining like terms in the i's and j's, or x hats and y hats if you wanted to use that notation. Now, note, by the way, that this is going to be in the third quadrant. So when we end up getting the angle, we're going to need to add 180 degrees if we end up deciding to take the arctangent of that. So that's just something we're going to keep in mind. So now we have our net force vector overall in component form. This is the net force vector in component form. So Pythagorean theorem this. Square magnitude to take the square root. That's worth a check. And then you get your final magnitude of 0.53 newtons for the force. What about the direction? Well, again, if you take the arctan of this, the arctan, depending on your calculator, is either going to be either in the fourth or the first quadrant for the angle itself, or the first or the second quadrant. Either way, I know that my two minuses would end up canceling and the calculator would think that it's in the first quadrant. Not. You need to add 180 degrees because the arctangent function, remember, is only defined up to multiples of 180 degrees. Or I should say it's indeterminate up to multiples of 180 degrees. So plug in got to check for simply either taking the arctan correctly in terms of the components of the force, or arcsine or arccosine if you ended up deciding to do it that way. I figure arctan is a lot easier. And then the next check is for getting the correct answer after doing that. So there we are. We have a total of 15 checks. Now, you also could have stated your angle other ways. If you just stated the angle directly as 265.3 degrees thereabouts, or 265 degrees, then it is assumed that that's a polar angle. If you did not identify specifically what the angle was, it is assumed that it's a polar angle. I highly recommend you on the AP exam to make sure you're identifying exactly what angle it is you are solving for. When they ask for direction, tell them, what do you mean by that direction angle? Like direction with respect to what? So in this case, I probably even should have been more specific. I should have said, comma, with respect to the positive x-axis going counterclockwise, but that's what we mean by polar angle. You also could have said 4.7 degrees to the left of the negative y-axis, or 85.3 degrees below the negative x-axis. Okay, now, what about the alternative solution? I noticed that while I was going over these that most students ended up actually solving this in some way with this alternative type of solution, which I highly recommend for what we are soon going to be doing with continuous charge distributions. So with discrete charge distributions, in other words, you have a few charges that are affecting each other. In my opinion, it's actually probably better to use the unit vector approach. It's usually cleaner, you don't have to remember as much, you don't have to do as much geometry and keeping track of signs, as long as you know what you're doing. But you do need to master the geometric trigonometric method involving sines and cosines and individual components, because that is going to be the much better method when we get to the continuous charge distributions that we're going to start dealing with soon in chapter 26. So here goes. Here's how we would do it alternatively. The first few checks are pretty much the same as before, writing givens, the free body diagram, and making sure that the sizes of the unit vector, or the sizes of the force vectors, are that they make sense, that F12 is bigger than F13. So again, we note the superposition principle. This actually is the superposition principle. I probably should have given this a check, because you would need to say that you're doing this, because saying that you're using the superposition principle as part of getting your answer is kind of an essential thing. I probably should have given that a check in both methods. So in any case, the result of this is that the x component of your net force is equal to the sum of the individual x components, and the y component of your net force is equal to the sum of the individual y components. How do you use that? You need to draw another diagram and put in angles, or at least put in angles on your original free body diagram. This check is for putting in angles so that people can see what you're doing. And these are 60-degree angles because the original drawing was an equilateral triangle. So here's what we have now. We need to, in order to get the force components in the x direction, we need to multiply each of our magnitudes by the cosine of 60 degrees. In order to get our, and in this case we needed a negative sign as well, because F12 is going down and to the left, so we're going to be taking the cosine of this angle to get the x component, which is going to be going that way, negative. We're going to take the cosine of this angle to get the x component this way, positive. That's what this first check mark is for. The second check mark is doing the same appropriate thing for the y components, and notice that it's, in each case, it's the sine of this angle and negative signs in front of there. If any of the negative signs are wrong, you don't get this check mark. Same with this one. Now, this next check mark is simply for noting what is Coulomb's law in terms of magnitudes. And this little n is just to denote that you can use any subscript, whether it's the charge 2 or charge 3 or whatever. So just if it's charge 2, then you plug in a 2 for n. If it's charge 3, plug in a 3 for n. In other words, it's the force on charge 1 due to the nth charge. and it's the magnitude of that force. So that's what this check mark is for, noting this with variables only. You probably used different notation, and that's fine. So now it's time to run some calculations. Well, plug the numbers into Coulomb's law for F12 and for F13 to get the magnitudes of each of those forces, and then multiply each of those by the appropriate sine and cosine term. Cosine of 60 degrees is a half, sine of 60 degrees is square root of 3 over 2. Again, you can get that from your unit circle. And that whole thing gets one big, fat, giant, bloody check mark. So next, we need to combine like terms. Combining like terms gets a check mark. Now we know our force components. You could actually write the force vector now. It's negative 0.0437 newtons I minus 0.5297 newtons J. At least to 4 sig figs. We shouldn't use 4 sig figs, but this is not the final answer. So then, you use the Pythagorean theorem, just as before, to find the magnitude of your force, and that becomes 0.53 newtons, just as it was before in the other solution method. And then again, easiest way to find the angle is take the arctan of the y component compared with the x component, and then you need to add 180 degrees, because remember arctan is indeterminate up to multiples of 180 degrees, and you know that this is in the third quadrant. So the result of doing that gives you a polar angle of 265.3 degrees, which again means that it's 4.7 degrees to the left of the negative y-axis, or 85.3 degrees below the negative x-axis. Saying any one of these answers would be fine. So that's the solution to the homework quiz, and please let me know if you have any questions. Thank you.